Welcome to the deep dive. Today, we're tackling something so well woven into the fabric of modern life, it's almost invisible: the internet and the World Wide Web.
Yeah, it really is everywhere.
We've got a fascinating collection of sources with us, and our goal is really to unpack for you just what this thing is. We'll trace its surprisingly dramatic beginnings and highlight some of the pivotal innovations that have shaped it.
Sounds good.
You, our listener, are looking to get informed quickly but thoroughly, so let's get right to it.
Indeed. So, at its heart, the internet, often just called the net, it's basically a global network of interconnected computer networks.
Right.
You can imagine it as this vast web where, with the necessary permissions, you can access information from virtually any other connected computer, and sometimes even interact directly with the people using those computers.
It's almost hard to believe, though, that this massive global thing had such, well, relatively humble beginnings.
Hmm.
Originally, as we see in our materials, the internet was primarily used to link laboratories doing government research. But then, from the mid-90s onward, it just exploded.
Completely. It impacted almost every corner of the world and fundamentally changed how we do business and, crucially, how we communicate.
That scale of change, it's really something.
What's truly remarkable is that sheer scale.
Yeah.
The internet has undeniably introduced this globalized dimension to our world. It's evolved into a universal wellspring of information for countless individuals, at home, in school, at work.
Its impact is almost immeasurable, really.
Yeah, it's huge.
And this is where it gets really interesting for me. This idea that the internet is arguably the most democratizing force in mass media.
How so?
Well, think about it. With a relatively modest investment, pretty much anyone can set up a presence on the web. That's a massive leveling of the playing field, isn't it?
That's a crucial point, yeah.
Hmm.
For businesses, regardless of their size or where they are, the internet offers this direct, rapid, and cost-effective way to connect with a potentially huge audience.
Exactly.
And for individuals, the hurdles to actually accessing the World Wide Web, the part we usually interact with, they're remarkably low.
So the mission for this deep dive is clear then. We aim to give you a solid and hopefully engaging understanding of the internet's fundamentals, where it came from, how it evolved, and the key bits that make it all work.
Right, the nuts and bolts.
Okay, so let's unpack this history. Believe it or not, we need to go back to the Cold War era.
That's right. Yeah, the story really kicks off in the late 1960s, specifically 1969, with the creation of ARPANET.
The ARPANET. Okay.
This was an initiative by the U.S. government's Advanced Research Projects Agency, or ARPA. The initial goal was quite focused: just enable researchers using computers at different universities to communicate.
Just communication between researchers.
Initially, yeah.
Yep.
And this shift, when administration later moved to the National Science Foundation, that wasn't just shuffling papers, it fundamentally changed the internet's purpose.
How so?
Well, it went from being this purely military strategic tool to one focused on scientific collaboration. And that, in turn, kind of laid the groundwork for it eventually becoming public.
Ah, okay.
It really shows how initial intentions can get dramatically reshaped by, what society actually needs and the new ways people find to use things.
And it wasn't purely about academic curiosity either, was it? I remember seeing in our sources that the ARPANET computers, they ended up being installed at universities that were getting defense-related funding.
Precisely. There was a definite strategic element. The U.S. government first started looking for nuclear war-proof communications back in 1960, briefing ARPA on it.
Wow, 1960.
Yeah. And the timeline shows things move fast.
Mm.
By '68, DARPA, that's the Defense Advanced Research Projects Agency, contracted with a company called BBN to actually build ARPANET.
PBN.
Then, 1969, boom, the Internet's ancestor was born, connecting those universities and researchers. By 1970, you had the first 5 nodes up and running: UCLA, Stanford, UC Santa Barbara, University of Utah, and BBN itself.
So it started as a kind of military pipeline, like one source put it, but gradually morphed as more academics jumped on board.
Exactly.
It's fascinating how it shifted into this communication tool, mainly for scientists. And then, like you said, management moved to the National Science Foundation, really showing that change in focus.
What's fascinating, too, is that ARPANET, implemented with these, pretty slow 56 kb communication lines.
56K.
Yeah, linking about a dozen universities and institutions. That became the undeniable grandparent of the internet we use today.
Incredible.
And while the initial aim was maybe sharing computing resources, letting researchers access powerful machines remotely, the unexpected but ultimately transformative benefit was fast communication between researchers.
Which was?
Electronic mail, email.
Okay, so email wasn't the original plan, but it quickly became the killer application. That makes perfect sense.
Totally.
Now, let's talk about the other foundational bits, those key innovations that built on this early network. Email was just the start, right?
Exactly. So 1971, Ray Tomlinson develops the first network email application, basically defining email as a program to send messages across this distributed network. That was a big leap.
A huge leap.
But yeah, the innovation didn't stop there.
What came next? I see a whole flurry of stuff in the early to mid-70s in our material.
Right. 1972, you get Telnet. That let computers connect remotely, more freely, more easily.
Telnet, okay.
Then 73, FTP file transfer protocol. That let computers send and receive data files.
Right, for moving files around.
And 74 was pivotal.
Huh.
That's when Vint Cerf came out with a TCP specification, a real cornerstone.
TCP. Now explain that a bit. TCP and IP are often mentioned together.
Yeah, think of TCP and IP as two layers working together. IP, the Internet Protocol, is like the postal service. It gets your message packet to the right address.
Got it. Address label.
Right. And TCP, Transmission Control Protocol, is more like a reliable delivery service. It makes sure all the pieces of your message arrive in the correct order and without errors. If something's missing, TCP handles getting it resent.
Ah, so IP finds the house, TCP makes sure the whole package gets inside correctly.
Exactly. A good analogy.
And it seems like the engineers themselves started realizing the potential was, well, way bigger than they first thought. There's a note about ARPANET engineers seeing potential for significant growth around 77.
That growing realization led to a really crucial technical change. In 1983, ARPANET actually switched from an earlier protocol, NCP, to TCP/IP.
That sounds like major surgery.
It's a fundamental architectural shift, yeah. But it's what truly allowed the network to scale up. Then the next year, 84, the domain name system, DNS, was introduced.
DNS, that's what lets us use names like google.com instead of numbers.
Precisely. Made accessing computers way simpler using memorable names instead of just those numerical IP addresses.
Okay, huge usability improvement there. And then we jump ahead a bit, late 80s, early 90s. This feels like the run-up to the internet becoming more mainstream.
Definitely. Tim Berners-Lee proposed a new set of internet protocols in 1989. And then in 91, the World Wide Web itself was developed and released by CERN over in Europe, initially within the UK academic network.
Ah, the www part we all know, developed at CERN.
That's the one. But the web was still, a bit technical to navigate at first.
Right. Not exactly click and go yet.
Not quite. The real catalyst for wider adoption came in 92 and 93 with Mosaic and then Netscape.
Mosaic and Netscape, I remember those.
Yeah, they provided a user-friendly graphical interface that made the internet far more accessible to the average person. Clickable links, images.
A total game changer.
Absolutely. And then 1995, a truly massive milestone, the U.S. government officially released the internet for commercial use.
And the floodgates opened?
Pretty much. That kicked off the massive expansion we've seen ever since.
It's remarkable how fast it went from, like, a research project to a global commercial platform. Okay, so we have the history. Now, how does this whole system actually work? What are the essential bits running behind the scenes?
Right, that takes us into the infrastructure and the standards that govern it all. It's not just chaos. There's a lot of coordination needed.
Coordination? By whom?
Well, key organizations like ICANN, the Internet Corporation for Assigned Numbers and Names, they play a huge role.
I can. What do they do?
They're a nonprofit, and they coordinate assigning things like internet domain names, those IP address numbers we talked about, protocol parameters, port numbers, all the unique identifiers.
So they're kind of like the global address book managers.
Or maybe air traffic control for the internet,
Yeah.
making sure everything has a unique spot and knows where to go. Yeah.
Okay. What about the other groups mentioned? IEPF and W3C.
Good question. The Internet Engineering Task Force, IETF, started back in '86. They're responsible for the technical standards of the internet. They produce these documents called Requests for Comments, or RFCs.
RFCs.
Yeah, and interestingly, they're all publicly available online. They detail exactly how various internet technologies should work.
So they write the technical rulebook.
Pretty much. Then there's the World Wide Web Consortium, W3C. Their focus is specifically on the web part, HTML, CSS, all that stuff. They develop recommendations and prototype technologies to standardize how the web works through specifications they call recommendations.
Okay, so ICANN for names and numbers, IETF for the internet's technical rules, W3C for the web's rules. Got it.
You got it.
Now, what about the actual physical structure? I see terms like internet backbone and NAP in our stuff. What are those?
Okay, think of the internet backbone like the superhighways. These are the really high-capacity communication links carrying enormous amounts of data between major regions, the big pipes connecting everything.
The interstates of the internet.
Exactly. Now, to get onto these superhighways, you need access points or junctions, usually in major cities. These are called network access points, or NAPs.
NFPs, the on-ramps and off-ramps.
That's a great way to think about it.
Yeah.
Our materials highlighted these are the biggest data connections on the internet, needing incredibly fast, high-performance servers and routers.
Okay, backbone for long distance, NAPs for the major connections. Makes sense. Now let's drill down to how my computer talks to a website. The client-server model comes up. What's that about?
At its core, the client-server model is just about a relationship between two computer programs, the client and the server.
Client and server.
The client is the one asking for some kind of service, maybe a file, maybe access to a database. The server is the one that fulfills that request and sends the results back to the client, usually over a network.
So it's basically a request-response system.
Fundamentally, yes.
Can you give us a real-world internet example?
Absolutely. Every single time you browse the web, that's the internet client-server model in action.
Yeah.
Your web browser, Chrome, Safari, Firefox, whatever.
Right.
That's the client. When you type in a web address and hit enter, your browser sends a request to a web server. That web server is the server in this model.
Okay.
The web server then finds the web page, grabs all its bits, images, text, code, and sends them back to your browser, the client. Your browser then puts it all together and displays it for you.
Okay, so my browser is the client, always asking. The website's computer is the server, always answering. Simple enough. Client requests, server responds.
That's the essence of it.
But our sources break down the client and server roles a bit more. What does a web client actually do?
Right. So a web client, like your browser, typically only connects to the internet when it needs something. It runs that browser software, uses HTTP Hypertext Transfer Protocol to talk,
HTTP?
and connects to servers using those URLs, the web addresses. Its main job is to ask for web pages and files, receive them, and then display everything formatted nicely so you can read it.
And the web server on the other side is always on, always connected, right?
Exactly. It runs web server software. Common ones are Apache or Microsoft's ISA. It also uses HTTP. It's constantly listening for those incoming requests for web pages.
Waiting for someone to knock?
Yeah. And when it gets a request, it responds. It sends back a status code like, okay, here it is, or sorry, couldn't find it, along with the actual web page and all the associated files needed to show that page.
Got it. Client asks, server answers. Cool. Now let's zoom out a bit from that specific interaction. How do all these devices get connected in the first place? That brings us to computer networks.
Precisely. Yeah, at its most basic, a computer network is just a bunch of computers connected together so they can share information and resources.
Share stuff like printers.
Exactly. Printers, software, data storage. The connection lets data move between machines, lets users share hardware, files on servers or in the cloud, even share software remotely or get updates.
And we use these networks for basically everything now, don't we? Communication, like email, video calls.
Absolutely. It's all built on these networks. And the concept of a node or workstation is key here.
A node.
That's just an individual computer device on the network. Could be connected with a cable, usually Ethernet or wirelessly with radio waves.
Like my laptop.
Your laptop, your desktop. And as our sources point out, this idea of a node has expanded. Your tablet, your smartphone, they're nodes too.
So my phone sitting here is just another node on this huge network. That's kind of mind-blowing.
It is, when you think about it.
Now, when we talk networks, there are all these acronyms flying around: LAN, PAN, WAN. What's the difference between all these types?
Okay, yeah. These classifications mostly depend on the geographical area the network covers. The smallest is a PAN personal area network.
Personal. Like just me.
Pretty much. Covers the immediate area around you. Think your phone connected to your Bluetooth earbuds or your home Wi-Fi connecting your personal laptop and tablet. That's a PAN.
Okay, PAN is tiny. What about LAN? That sounds familiar.
LAN is local area network, usually covers a single building or maybe a small campus. It's a collection of computers, printers, all linked together, often sharing one internet connection.
Like an office building or a university department.
Exactly. Those are good examples of LANs.
Makes sense. Then we have MAN and WAN, which sound bigger.
They are. MAN is Metropolitan Area Network. It's bigger than a LAN, might cover a whole town or city. Your local internet service provider might operate a MAN.
Okay, city-sized. And WAN.
Wide Area Network. That's the big one. WANs link machines over large distances, even globally. They use long-distance transmission lines. Think of big international banks connecting their offices worldwide. That's typically done with WANs.
So PAN, personal, LAN, local, MAN, metro, WAN, wide world, got the scale. But our sources say the internet itself isn't just a typical WAN, even though it's global. Why is that?
That's a really important distinction, yeah. While you could loosely call the internet a massive WAN, it's much more accurate to call it a network of networks.
A network of networks.
It's incredibly complex, unique in its hardware and software. It connects billions of devices worldwide. It doesn't really fit neatly into those simple geographical boxes.
Yeah.
It's truly considered one of humanity's major technological achievements.
That puts it in perspective. It's not just a big network, it's the network that connects all the other networks. Okay, so devices are connected. How do they talk? That's protocols, right?
Absolutely. A protocol is basically a special set of rules.
Mm.
It defines how network connections are used when devices want to communicate. The rules specify how they interact.
Rules of the road for data.
Pretty much. And in the standard networking models, you often have multiple protocols working at different layers to make sure communication is smooth.
Our sources mention Ethernet a lot, especially for LANs and MNs. What exactly is Ethernet?
Ethernet is a whole family of networking technologies, super common in those local and metro networks. Essentially, it's a protocol that says how network devices should format data to send it to other devices on the same network segment.
So it's how my computer talks to the router via cable.
Very likely, yes. You're probably using Ethernet. The common standard you see is often 100 base T, using those twisted pair cables like KT5 or KT6 with the little plastic RJ45 connectors. That gives you speeds up to 100 megabits per second.
Right, those familiar network cables.
Yeah. Most are wired to connect a computer to a router or a switch, but there are also special crossover cables if you want to connect two computers directly, though that's less common now.
Okay, so Ethernet is the workhorse for local wired connections, but the internet as a whole, that's TCP/IP, right? You mentioned it's the basic language.
You got it. TCP/IP Transmission Control Protocol Internet Protocol really is the fundamental communication language, or a suite of protocols, for the internet. And it's used in many private networks, too.
So every device needs it.
If it wants to connect to the internet, yeah. Your device uses a copy of TCP/IP to send and receive messages. We touched on it before. TCP handles breaking messages into packets and ensuring reliable delivery.
Making sure everything gets there in order.
Right. And IP handles the addressing part, making sure those packets get to the right destination across the internet.
So TCP for reliability, IP for addressing, that helps. Are there other really key protocols we should know?
Yes, definitely. HTTP Hypertext Transfer Protocol is absolutely crucial for the World Wide Web.
The HTTP at the start of web addresses.
Exactly, or HTTPS for the secure version, which is much more common now. It's the protocol used for transferring HTML documents, the web pages, between your browser and the web server.
Okay, HTTP for web pages. What else?
And then there's FTP File Transfer Protocol. As the name suggests, it provides rules for transmitting files between computers over the internet. Less common for casual users now maybe, but still important underneath for some things.
So HTTP for web pages, FTP for files. Got it. Now, when I want to go to a website, I type in that address.
Right.
That's the URL, right? How does that fit in?
Exactly. URL stands for Universal Resource Locator. It basically contains all the info your browser needs to find and contact the right server and ask for the specific thing you want, usually a web page.
It's the full address.
Yeah. Our sources gave an example. It includes the protocol, like HTTPS, the domain name of the server, like www.final.edu.tr, and then the specific path to the resource on that server. UFU7 Academico 1 faculties.
Yeah.
The roadmap to the content.
Okay, URL equals roadmap. Now, I've also heard intranet and extranet. How do those relate to the internet?
Good question. An intranet is essentially a private network. It's like a mini internet just for computers within a specific organization. It's not accessible from the public internet outside.
Internal only.
Right. An extranet is also a private network, but it's designed to allow some controlled external access. So certain authorized users or devices from outside can connect to it, usually via the internet, but it's not wide open like the public internet.
So intranet is locked down internally. Extranet has a controlled door for specific outsiders.
That's a good way to put it.
Okay. Now, every device needs a unique identifier, right? That's the IP address.
Yes, the IP address, Internet Protocol address, is that unique numeric identifier assigned to every device connected to the internet.
The string of numbers.
Exactly. The most common format you see is IPv4, but we're running out of those. So there's a newer version, IPv6, which offers a vastly larger pool of addresses. They actually coexist right now.
IPv4 and IPv6. And our sources mention Google's public DNS addresses as examples.
Yeah, 8.8.8.8 and 8.8.4.4, those are well-known IPv4 addresses. And you can actually find your own computer's IP address pretty easily.
How?
On Windows, you open the command prompt and type ipconfig. On a Mac or Linux, you open the terminal and type ifconfig. It'll show you your local IP address.
Ipconfig or ifconfig. Handy. And remembering those long numbers would be impossible, which is where domain names like www.google.com come in.
Precisely. Domains technically are defined by those IP addresses.
Yes.
Devices sharing a common part of the IP are in the same domain. But yeah, since numbers are hard for us humans, domain names like google.com are linked to IP addresses through the DNS, the domain name system.
DNS translates the name to the number.
Exactly. Makes life much easier. And it's worth noting, a single domain name can actually point to multiple IP addresses, maybe for load balancing or different servers. So the specific IP you hit might change.
Okay, domain name, friendly face, IP address, actual location. Lastly here, open versus closed networks.
Right, an open network is basically public domain. No real control over who connects. Think of a public Wi-Fi hotspot with no password.
Anyone can jump on.
Yeah, a closed or proprietary network is owned and controlled by someone, an individual, a company. Access is restricted. That cafe Wi-Fi that needs a password, that's a closed network.
Okay, clear difference. Open for all, closed with controlled access. Right, let's move on to how these networks are actually, well, laid out, structured. I see an analogy about an army needing order. Brings us to network topologies. What's that?
Network topology is just the pattern, the orderly way the nodes, computers, devices in a network are physically or logically connected, how the network is arranged. It's especially important in LANs.
The layout plan.
Exactly.
And there isn't just one layout, right? Our sources list a few common ones.
That's right. There's the ring topology where devices connect in a closed loop, kind of old school now.
Mm-hmm.
Then there's BUS or line, where everyone connects to a single main cable, also less common for new LANs.
Ring bus. What else?
The star topology is very common. All devices connect to a central point, like a switch or a hub. Then you have MEH, where devices connect to multiple other devices, creating lots of paths, very resilient but complex.
Star sounds familiar. Mesh sounds robust.
Any others? And tree, which is basically like linking multiple star topologies together. An extended star, really.
Wow, quite a few options. Is there a single best topology?
That's a great question. And the answer is not really.
Depends.
Yeah, like mesh sounds great for redundancy. If one link breaks, data can find another way. But it's often the most complex and expensive to wire up and manage.
Makes sense.
Star topology, using a central switch, is very popular for practical reasons.
Yeah.
It's easier to add new devices, easier to troubleshoot, although the central switch is a single point of failure.
Ah, a trade-off.
It often is in network design. Central control versus potential single points of failure. Bus topology, for instance, if that main cable broke, the whole segment could go down. Star makes finding problems easier.
So reliability, cost, ease of management, it all factors in.
Exactly. As our sources say, there's no single best. It depends on the specific needs and budget for that network.
Right, find the right fit for the job. Now, if I wanted to set up a simple network, say at home, what basic hardware would I need?
Okay, our sources list the essentials. You definitely need network cables, those Category 5 or Cat6 RJ45 cables we mentioned.
Yeah. Wired is still better sometimes.
Generally, yes. Wired connections are usually faster and more reliable than wireless because radio waves can be unpredictable, interfered with.
Okay, cables. What else?
You'd likely need a distributor, typically a switch these days, maybe built into your router to connect multiple computers together, maybe a dedicated router if you need more advanced features, or to connect different network segments.
Switch or router.
And then your devices need network interface cards, or NICs. These might be built into the motherboard, or they could be separate cards you install, or even external USB adapters, especially for wireless.
So cables, a switch router, and network cards for each device.
Got it. What's the real difference between a hub, a switch, and a router? They all sound like connection points.
That's a common confusion point. A hub is the simplest, oldest type. It's dumb, basically. Data comes in one port, it just blasts it out all the other ports. Not efficient.
Okay, hub, loud broadcaster. Pretty much. A switch is smarter. It learns which device is connected to which port by looking at the traffic. So when data comes in for a specific device, the switch sends it only out the port connected to that device. Much more efficient.
Switch, targeted delivery.
Right. And a router is the smartest. It's designed to connect different networks together. It can understand IP addresses, make decisions about the best path for data to travel, and potentially do things like block certain traffic. Many home routers today also include a built-in switch and wireless access point.
So, hubs broadcast, switches direct traffic within one network, routers connect different networks and make routing decisions. Clears that up.
Good.
Our sources also mention firewalls alongside hardware. What do they do?
A firewall is all about security. Its a system could be hardware, could be software, could be both, designed to prevent unauthorized access to or from a private network. It acts like a security guard at the gate,
Keeping bad stuff out.
and sometimes keeping certain stuff in. Importantly, when your home router performs NAT network address translation, which hides your internal device IPs from the public internet, it's effectively acting as a basic firewall itself.
Ah, so my router probably has a firewall built in.
Most consumer routers do, yes.
Mm-hmm.
That NAT function provides a fundamental layer of security.
Good to know. Okay, finally in this section, we've talked mainly wired networks. What about the mobile networks our phones use? Cellular.
Right. Mobile or cellular networks are communication systems where that last connection, the last hop to your device, is always wireless. They use radio frequencies within specific geographic areas called cells.
Cells, hence cellular.
Exactly. And these networks are run by mobile network operators.
Yeah.
Your phone company, basically. We're all familiar with 3G, 4G, 5G.
The G's, what's the difference?
They represent different generations of mobile tech. The main difference people notice is speed and capacity. 4G was a big jump, bringing true broadband speeds to phones, making video streaming practical.
Right, 3G was much slower.
Yeah. And 5G, which is rolling out, offers even faster speeds, lower latency, and more capacity.
Right.
Plus new underlying technologies that enable new applications and support way more devices connecting simultaneously. Each generation usually brings new tech, more capacity, sometimes better voice quality too.
So our phones connect wirelessly to cell towers, and those towers connect back into the main internet infrastructure.
That's the basic idea, yes. It's all interconnected in the end.
Wow. Okay. Well, we have covered a huge amount of ground in this deep dive. Let's maybe try and summarize the key takeaways.
Absolutely. Sounds good. We started with the internet's origins, right? Back with ARPANET, that research network.
Yeah, Cold War roots, connecting researchers.
And its evolution, driven by key inventions like email, TCP/IP, DNS, the World Wide Web.
And browsers like Mosaic and Netscape, making it usable for everyone.
Exactly. We then looked at the infrastructure, the massive backbone, the NFPs connecting things up, and that fundamental client-server model that powers browsing.
My browser asking, the server answering.
Right. We also touched on the different types of networks, PAN, LAN, MAN, WAN, and how the internet is really this unique network of networks.
Not just a big WAN.
Correct. And finally, we dug into the protocols, the rules, like Ethernet for local connections, and the vital TCP/IP for the internet itself. Plus, addressing with IP addresses and domain names, and the basic hardware like cables, switches, routers, and firewalls. Oh, and mobile networks, too.
Phew.
Yeah.
It's a lot. And it's still just kind of amazing to me that something so integral, so fundamental to modern life, started with that relatively narrow goal of connecting researchers and, almost weirdly, needing to survive a potential nuclear war.
Yeah, the way it evolved was definitely not planned out from the start.
Right.
Its impact is staggering, really, unexpected.
It really is. It makes you think about how these foundational technologies can just take on a life of their own, doesn't it?
For sure. Transformative in ways the originators probably never imagined.
It does. And, that brings us to our final thought for you, our listener. Thinking about that initial democratic promise of the internet, low barriers to entry, sharing information,
Yeah, that early vision.
and comparing it to today with its incredible complexity and, let's face it, a lot of centralization around big players, what future changes might actually further that original democratic idea? Maybe decentralized tech, community networks.
Or the flip side.
Or the flip side, what new challenges might actually threaten that vision? Especially when you consider the massive differences in tech access and infrastructure around the world, could that actually widen existing inequalities?
That's a really important question. Does the tech divide grow or shrink?
Exactly. Something to really mull over as we navigate this increasingly connected world. Thanks for joining us for this deep dive.